Hello everyone, my name is Sinan Topçukar and today together with my project partner Eren Korkmaz under the supervision of Professor Dr. Nefsime Hensel Yükselerdem, we will be presenting our project, Material Classification Using Thermal Characteristics. Our project is focused on classifying metal, plastic, glass and paper products. Each of these materials has a different specific heat capacity, so the patterns in their heating and cooling cycles are distinct. These patterns can be learned by artificial intelligence and used to design a recycling classifier. And this is pretty much the fundamental basis of our work. Now I'll hand the presentation over to Eren Kok.
As you can see, we have mounted and stabilized both the thermal and electro-optic cameras on a custom-built structure. On the left side, you can observe the thermal camera in operation. At this stage, we are simultaneously monitoring both the conveyor belt and the heater. Throughout all of our experiments, the conveyor belt speed and heater power were kept constant to ensure controlled and repeatable environment, as well as a controlled experiment. As the heater operates, you can observe the heating process within its active range. We allow sufficient time for the background to reach thermal equilibrium assisted by the continuous motion of the conveyor belt. Now, what you are seeing are the samples used in our dataset, various waste materials we have collected encompassing of all of our categories, metal, glass, paper, and plastic. Each category involves diverse objects, some of which may appear ambiguous to the naked eye and could easily be misclassified without thermal analysis. Finally, here's a short demonstration showcasing the whole system in action. Introduction of our experimental setup, we now delve into the technical details. Since our system utilized two different types of cameras in terms of resolution, recording angles, and etc., it was essential to address both spatial and temporal alignment between them. Why do we need temporal alignment, you may ask? Sometimes our thermal camera enters the NUC states, where it automatically adjusts itself. During that process, unfortunately, camera stops for a couple seconds. To achieve this synchronization, we thoroughly investigated and evaluated several calibration methods, aiming to ensure correspondence across both modalities. We extensively synchronized literature research to determine what's the standards. So first we start with the marker board calibration pattern. We applied our situation. Then we try to implement cardboard, acrylic calibration board, wood and vinyl calibration board, metal and vinyl calibration board. Each calibration board has a disadvantage and advantage among them in terms of constructions and limitations. After we trying each and every one, we concluded that we need less and meaningful key points rather than more key points, which means key points should disperse equally across the x and y axis respectively. As you can see here, in this calibration pattern, we would not obtain a good result in a warp image. You can see they are not looking similar. And we also examined the MATLAB's preferences about the calibration patterns, and we tried to apply them too. As you may see from here, we tried each and every one of them, and we concluded this is the most important calibration pattern for us. As you can see, the matchings in both images, this clearly outweighs the other one. Another important point in our project is to find and match the key points, because the performance of how well we would obtain the output results is highly dependent on how well we are finding and matching those key points. All the documents have been produced by us and will be added to the descriptions if one demands. Those documents explain how are the things being handled background mathematically. For sake of the length of the video, we would not point out those entirely, and we reflected our knowledges to those documents for better understanding. So basically, we tried the traditional feature detection and matching methods such as SIF, SURF, ORB. Those are like, we know those are old, but they're often used in the industry. So we implemented those too, and we compared with the superpoint and superglue algorithm. And as you can see from the quantitative advantage of superpoint and superglue, even the most popular one, SIFT, cannot outperform the superpoint and superglue. And with the inspiring by those algorithmic things, we try to come up with our own algorithmically minimizing distance algorithm, matching algorithm, but it cannot outperform superpoint and superglue. So how and when we are using superglue and superpoint algorithm to match thermal camera and RGB camera, to key points, find the key points. And from this picture, you can see when we lower the threshold, match threshold, it finds a lot of key points, which is not applicable in our situation, as I have mentioned earlier. We need less and meaningful key points. As you can see, let's look at this one. This one says this matches with a lot of points in RGB, but it's not at this point correspond to this point. As you can see, it couldn't find the perfect matches, so it's trash. So, but if you look at this thing, as you can see, it matches perfectly, and we obtain what we entirely need. So after pre-processing and trying with maybe thousands of data, we concluded that those are most of the time doing all right, those values. So conclusion, the superpoint and superglue represents significant advancement over traditional methods. It provides global context awareness, superior cross-model matching capabilities, and robust performance, which the others cannot. Because it's nearly impossible to construct ground truth labelings on thermal camera because of the low resolution, our strategy was to label them on RGB side and overlay to the thermal camera domain. So in order to do that, we fine-tuned the Detecton dataset. And what is the Detecton dataset? Is an object detection and segmentation framework developed by Facebook AI Research. How would we be doing this framework? We first collect our RGB data and pre-process them to feed them into the Make Sense AI, and then we with our hands, we label them by each, and we export annotations with the Coco JSON format. Then we train our own model and make the guesses. So manual annotation process will be displayed after this thing on Make Sense AI. This is the Coco format structure. It gives exact locations where it has been annotated and for which class it has been annotated to. Those things are can be differ. For example, you can change the max iterations and batch size and etc. But our project, since our project mainly focuses on the thermal side, those things are not that much important for us because we only want to fine tune the data to construct the grand truth things. So as you can see, for evaluation metrics, we use intersection over union and mean intersection over union because it more fits into our situation. So let's see some visualization and experimental results. As you can see, you can stop and look at the images by yourself. It predicts very well, and it predicts with a high percentage. For example, it says 83%, in here 99, 94. It is great for us already. You can stop and look at the pictures if you want to. And for the material classification performance, we threshold with 0.5 intersection over union because we wanted only the meaningful ones. As you can see, we obtain very good results for RGB side. And as well as for quantitative evaluation with the baseline metric, which is a detector on dataset itself, it gives 0.4 mean intersection over union, which is really, really low, and we improve that over 60%, which is really good and desirable. And for notation, this has been constructed with approximately 100,000 frames. It is more developing right now. So conclusion, we used Detect on Dataset and Make Sense AI. Discussed it earlier, every application we have done, we did in RGB domain. Because of the detect and the track objects regarding to obtain their thermal characteristic cycles in thermal domain is nearly impossible due to low resolution and frame contrast. But our project mainly focuses on the changing thermal characteristics, not in RGB segmentation. So we have to overlay everything in RGB onto thermal. In order to accomplish that, we dealt with both spatial temporal alignment. Let's start. So the challenge of dual model alignment basically consists the resolution disparity, field of view differences because of the angles that we put in, feature correspondence, temporal synchronization, and thermal camera artifacts. So requirements for material classification is both spatial and temporal consistency, right? So we try to come up with that. To solve the problem in spatial alignment, we use SuperPoint and SuperGLUE pipeline, as we have mentioned it earlier. So we match both of the frames and obtain the homography matrix. If we multiply homography matrix with the frame, we would obtain the thermal correspondence of that specific frame. And if we apply this to every frame in the video, we would obtain the thermal overlay version. For the temporal alignment, first we use the dynamic time warping algorithm. This is a mathematical formulation, but we have encountered with some limitations that we cannot change. Well, one of them was timestamp accuracy. Unfortunately, our thermal camera cannot provide us the correct timestamp, so we cannot work on them. And the other one was non-uniform frame rates, which is we expected to record the video with 30 FPS, but sometimes the mean FPS is around 28, 29, 27, which disallowed us to work perfectly. And the last one is interruptions due to the NUC. When it comes to NUC states, sometimes it stops too much and we are losing too many timestamps. Let me show it with the example. Okay. So this is the RGB and this is a thermal frame. As you can see, they are not even remotely similar. So another key point algorithm that we use is SuperPoint and SuperGLUE. What we do is we take a reference frame for the electro-optical camera, and we search it from the thermal video. This search window and search center is adaptive. It adapts itself to looking at the signal to noise ratio. Sometimes we are searching 20 frames, 50, 100. It adapts itself. This is important because when it comes to NUC states, it has to adapt itself. And we are finding the best matches using SuperPoint and SuperGLUE and matches those frames as they're similar. As you can see, this is mean distance. It's about 50 pixels. It's very less. It's considerably good. And this is the warp RGB frame and thermal frame. As you can see, they're very, very looking similar. But the problem with this method is actually important, and it has some drawbacks because when it comes to NUC events, we cannot sometimes do our job perfectly, and it's computationally expensive job. Sometimes processing the 50-minute video required 3 to 2 hours with a good GPU.
As you can see, detections produced by Detectron 2 play a crucial role in the segmentation phase of our project. However, these detections must merge into a multi-object tracker. In this way, the information for each object is preserved over time and the dataset becomes ready to feed into a sequence-based neural network. In the tracking algorithm, the following steps were followed. First, we computed the centroid of each Detectron 2 detection and labeled every newly detected object as tentative, aiming to reduce errors from false alarms. In the very next frame, we compared distances between current detections and those from the previous frames, then applied the Hungarian algorithm to associate detections into tracks. If a detection belonging to a tentative track could not be matched with any new detection in the step, then that tentative track was deleted. In every subsequent frame, the tracker runs an algorithm that minimizes the distance between matched detections across consecutive frames. every newly observed object is initialized as tentative track. If a tentative track fails to be confirmed, it is deleted, and a track becomes confirmed when it has been detected for a specific number of consecutive time steps, and this confirmation loop then continues. To guard against misdetections, once a track is confirmed, it must still be detected in at least 7 out of 10 frames in order to remain confirmed. And when a confirmed track is not detected in a frame, we assume that the object has a constant velocity, and by using that assumption, we update the bounding box positions and segmentation masks. And by using that, we actually don't need to use a Kalman filter. And after performing all of those operations in RGB domain, now what we have to do is to map those processes into the thermal domain, and we perform that task by using SparePoint and SpareGlue. That framework gives us an homography matrix, and by using that homography matrix, we map the RGB video to the thermal one. And here, as you can see, the left hand side is the warped RGB video, and the right hand side is the thermal video. We basically map the RGB video into the thermal one. And after that, once the full dataset is assembled, then what we have to do is the material classification using thermal characteristics. We have metal, plastic, glass, and paper, and based on their thermal signatures, we will classify them. But what are those thermal signatures? What are those significant features that will help us? Well, in metal objects, we have some sudden changes. They heat up more quickly and often exhibit multiple peaks in their temperature curves. As you can see here, we have one peak, two peak, one peak, two peak. It has some multiple peaks, and like I said, it's heat up quickly. For glass, as you can see, the maximum values for the glass samples are relatively low, which indicates they never heat up sufficiently during their warming phase. And plastic, we have a sudden peak. Also, we have a sudden peak in paper, but the difference is paper clearly takes longer to cool down. And additionally, the maximum temperatures of paper samples do not reach the same heights as those of plastics. And to make a classifier, as a first step, before applying sequence-based classification models, we extracted salient features, the minimum, maximum, mean, and variance values, as well as the heating and cooling durations. We will use all those features to build up a decision tree, and we will use it as a baseline. Here we have the decision tree implementation. Here is the feature visualizations. Let's take a look at this one. The green ones are papers. This one is plastic, metal, and glass. They have their own boundaries. Also, again, we have glass here, paper, plastic, and metal. And by using the combinations of these important features, the decision tree models can actually classify them pretty accurately. Here are the results. We have nearly 82% accuracy, which is not bad for a start, but of course our goal is to increase the accuracy by using some advanced models. And what are those advanced models? Inception time, Rocket, ResNet, HaveCote 2.0, LSTM models, GRE models, transformer encoders, etc. Here we have the HaveCote 2.0. The accuracy is 87%, which is okay, but we have to take something into account that we don't have yet processed all the data, so our data set will grow a little bit, it will be larger, and we will also use some fine-tuning methods to increase the accuracy. And all these techniques are still under development, and like I said, because we have not yet processed all the videos, Current accuracy rates vary between 70% to 80%. And our ultimate goal is to perform a comprehensive comparative analysis. We will compare most of the time sequence based classification models, and we will provide a comprehensive comparative analysis. And that will be our work. And in the end, we want to publish an article about our outputs. And this is all for our project. Thank you, everyone.